NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, folks, wherever you may be. I am Brian White from JPL's Office of Communications and Education, and welcome to the Von Karman series. The Von Karman Talks are a monthly opportunity to engage with you, the public. This is your space program. Now, as a reminder, as we're going through tonight, if we have any technical difficulties, we ask your patience as we get them sorted out. Tonight, we'll be exploring the outer moons, what they're doing out there, and what their orbits have to do with us here at home. As always, you are a big part of these discussions, and joining us as our questions co-host tonight is Lindsay McLaurin. Hi, Lindsay.
Hello, Brian, and welcome everybody. As a reminder, this is your space program, and we want you to be involved with tonight's discussion. So for wherever you're joining us, please use our chat feature to ask questions, and members from our amazing social media team will pass them along to us. If for some reason you don't see the chat feature, please refresh your page, and it should be there shortly. Let's get started, Brian.
Thank you very much, Lindsay. I'm looking forward to hearing those audience questions here in a bit. Now, our speaker tonight is a radar scientist and an orbital dynamicist from NASA's Jet Propulsion Laboratory in Pasadena, California. Dr. Brozovic observed hundreds of near-Earth asteroids with the Goldstone and Arecibo planetary radars. She was involved in the discoveries of binary and triple asteroid systems, 14 moons of Jupiter, and several trans-Neptunian objects. A main belt asteroid, 7295 Brozovic, is named after her. Her research also involves tonight's subject, orbital dynamics of the moons of the outer planets. And she worked on NASA's New Horizons mission to the dwarf planet Pluto as a part of the Hazards team. She received her undergraduate degree in physics at the University of Zagreb in Croatia and her PhD in physics from Duke University. She spent several years at Caltech as a postdoc before joining JPL. Please welcome Dr. Marina Brozovic. Hi, Marina.
Hi, Lindsay. Hi, Brian. Thank you for inviting me. It's really a pleasure to be here.
Well, thank you for being here. And we're going to start with the basics. What is it that we consider satellites of the older system? How do we find them? Where do we find them? What is their origin?
Well, the most basic definition of a satellite is just a small body orbiting a large body. And the small bodies that I want to talk about are actual natural satellites of planets. And we find these objects within planetary Hill sphere. And planet's Hill sphere is just basically a region of space where planet gravity dominates the sun gravity. And the size of these Hill sphere, it depends on how massive the planet is. And actually, let's go to our first slide. And so it depends how large the planet, how massive the planet is, and how far away it is from the sun. So here we see kind of visual comparison of the Hill spheres of the planet. Jupiter, despite being the most massive planet, does not have the largest Hill sphere. That goes to Neptune, which is still a fairly large planet, and it's very far away from the sun. And so it has this really large region of space where it could potentially have its satellites. And you see that the size of its Hill sphere is almost 3/4 distance from Earth to the sun. So really, really large space. And going back to your question about origins, well, their orbits and the sizes of satellites, they tell us, they kind of give us a hint. So let's go to perhaps next slide, where I'm just going to go over three basic groups of the planetary satellites. So we have the regular satellites, we have the inner satellites, and we have the outer moons, or sometimes called the irregular moons. And I'm going to start with basic. We are all familiar with the regular satellites. Those would be like the Galilean satellites of Jupiter. So these are kind of massive spherical bodies that are orbiting the planet in almost perfect circles, and they are along the equator of the planet, and they orbit in the same direction as the planet spins. And they formed with the planet itself from the circumplanetary nebula. And then inner to these regular satellites, we have the inner satellites, and we sometimes call them the collisional shards, because they probably used to be regular satellites that had ground down to smaller pieces, but they still have these nice circular orbits. And then when you see these weird orbits marked in red, these are the irregular satellites. They orbit from huge distances from the planet. Their orbits are anything but circular. They are, very elongated. They're not anymore aligned with the planet's equator. And they know to orbit the planet in the opposite direction that the planet is revolving around the sun, which kind of gives us a strong hint that these are not native to the system. These are actually captured objects. Presumably, they used to orbit the sun, and at some point they came too close to the planet, and it's just basically planet gravity caught it. And the dynamicists are still kind of debating exactly on which mechanism is the best to capture an object. And also there are a lot of puzzles about their kind of source region. We don't know whether these are captured asteroids from the main belt, or these are perhaps Kuiper belt objects, or there's something in between. And I really hope to kind of tell you a little bit more stories about the irregular satellites as we go through our kind of chat today.
Yeah, well, as you talk about how there's still some uncertainty with how they get captured, have we found all of the planetary satellites in our solar system so far?
Well, it's safe to say we definitely found all those big regular satellites, but we're probably missing some number of the inner satellites, and we're missing a lot of the outer satellites. So the current head count is we have 213 moons. These are acknowledged by the International Astronomical Union. And our job here at the Solar System Dynamics at JPL is to keep track of their orbits, so to calculate their orbits. So we're a little bit like, flight control for the solar system. And we depend on astronomers to observe them. And so let's take a look at the next slide. These are images from where we get our data. So to your left, you're seeing, this is example, these are inner moons of Neptune. And so what astronomers do, they have to kind of block this bright glare of the planet, and then they work really hard to dig out these really, tiny specks of light from the background. And they report to us measurements of their position with respect to central planets in time. And they have a little bit easier time with the outer satellites. You see here to your right, this is an outer moon of Jupiter. And you see this little bright glint as it's darting off across the stellar background. And in this case, they don't have to deal with the bright glare of the planet. They just kind of measure its position in time with respect to the stars. And now we have kind of, beginning of, we have all the data, all the ingredients that we can start doing our orbit fit.
You started to hint at your group and the people you work with. So let's talk a little bit about you and the Solar System Dynamics group. How do you calculate these orbits?
Yeah, so basically it's just physics. So I try to, let's go to the next slide, because this is where I kind of try to visualize our orbit fitting, what orbit fit really is. So basically you start with a dynamical model. So this would be an equation of motion that takes into account all the forces that are acting on the satellite. So this blue circle that you're seeing here, this is your dynamical model. And then what we also have are, look at these little balloons. These are our free parameters. And objective of the orbit fit is to adjust these free parameters so that your starting position and velocity of a satellite, that this blue dynamical model can correctly propagate it in time so that you can reproduce your measurements. And, we go through iterations, and we have these algorithms that are minimizing the difference between our orbits and the measurements at hand by adjusting these parameters. And you'll notice that some of the balloons are larger than the others because some of these parameters end up being more important than the others. And so when all this is done, I'll show you how, on the next slide, please. This is kind of how we evaluate the quality of our orbit fit. We are looking at the differences between our simulated data and the real data. And this is something we call residuals. And as an orbit fitter, we love our plots with residuals. There's no better way to show this. And I know when I give my technical talks, if I show more than 3 of these, I know I can put half of my audience to sleep. so I'm not going to do that. But I just want to mention that, the orbit fitting is important because you need to know orbits in order to tell a story and to understand the system.
You mentioned to me before we did this tonight that you've got some great animations of planetary systems. They're showing the real position of these satellites in time. Which one do you want to start with tonight?
Yeah, so what you're going to be seeing, I made some visualization, and these are real orbits. So you could be pointing your telescope or flying a mission based on orbits that you're going to see. We have to start with the system of Jupiter. So let's go to the next slide. And so here's Jupiter, and it really has 80 natural satellites. And what you're seeing here first, you have 4 Galilean satellites, Io, Europa, Ganymede, and Callisto. And then inner to these, you have these 4 inner satellites. And they're also connected with the system of faint rings that Jupiter has. They're strange objects. Some of them kind of resemble asteroids. And there are even some theories that they could be captured, but it's very difficult to explain how something captured could end up in this well-behaved circular orbit along the planet's equator. And what you're going to soon see, you're going to see where Juno spacecraft is right here. It's currently exploring the system of Jupiter. And then here, far beyond orbit of Callisto, this is where party starts. This is the realm of the outer moons of Jupiter. And there are 72 of them that we know of. So the ones in yellow, they are what we call the prograde moons. Basically, they're revolving around the planet in the same direction that planet is revolving around the sun. And the red ones are revolving in the opposite direction, so these are the retrograde moons. And the largest representative of these moons in yellow, it's called Himalaya. Quite large. It's about 140 kilometers in diameter. And it's related to some other members of this group in yellow. Basically, the idea is that once upon a time, this was a larger object that collided with something. And then we're looking at these shards that evolved into their own orbits. And similar story, you're looking at this yarn of red satellites. So believe it or not, there are like three families there that also presumably once upon a time were much larger body that got collisionally disrupted. And, we at SSD, we calculate the current orbits of these satellites, but there are dynamicists out there that spin these orbits backward and forward in time for millions, even billions of years, because they want to answer questions about their origin and their ultimate destiny. And there are always some interesting stories to tell. So I really want to draw your attention to this moon in white. It's called Valetudo. And that one is the outermost prograde moon. Basically, it is orbiting in a region of space where everybody else is retrograde. So it is kind of driving against traffic. And what dynamical studies are showing is that sooner or later it's going to cross paths and have head-on collision. And another thing we know about this moon, it's very small. It's about only maybe 1 kilometer in size, perhaps smaller. And it doesn't have any other piece that is related to it. So that kind of brings an interesting story, and that is that it's perhaps the last surviving member that got ground down to this tiny little piece and that ended up creating perhaps some of these big retrograde families in past head-on collisions.
I love Jupiter, but personally, I love looking at Saturn. And I know that Saturn has more moons than Jupiter. First off, am I right about that? And how do the rings of Saturn fit into this story about the satellites?
Yeah, okay, well, funny that I have an animation about Saturn. So let's go to the next slide. So you're correct. Saturn has 83 moons, natural satellites, while Jupiter has 80. The most obvious thing at Saturn are this huge system that, its rings. We think they originate from a disruption of a small moon some 100 million years ago. And even the current moons in the system, they still play a role in the life of rings. They're either responsible for these gaps in the rings, or they're actually source of material themselves. So let's take a tour here. You are seeing there are 24 regular satellites of Saturn. So the blue colors are the large satellites. So those would be like Rhea or Titan. And then in these light colors, these are tiny little guys. So that would be like Daphne or Atlas. And moon that is actually really interesting here is Enceladus. You probably know about Enceladus. It's spewing these icy particles, and it's a source of this very faint ring, which is stretching from the orbit of Mimas all the way to the orbit of Titan. So that is, the moons are really kind of interconnected and interleaved with a system of rings. And you're going to see, this is where Cassini used to orbit the system toward the end of its mission. And again, we are entering the realm of the outer satellites. The yellow ones, those are the prograde satellites, and this crowd of red ones are the retrogrades. Similar to Jupiter, we have several dynamical families. So again, presumably something much larger got collided, and the shards evolved into their own orbits. And we have another traffic offender. There is another little moon, this time with a poetic name, 2004 S24. So this one is the outermost prograde moon. It, again, probably, dynamically it could collide with some of the retrograde moons, and perhaps, it formed some of these retrograde families. And in fact, actually, when you mentioned how Saturn overtook the number of satellites from Jupiter, that happened in 2019, when there were 20 new satellites of Saturn announced. And basically, surveys are currently discovering at Jupiter satellites that are, say, about 500 meters, so really small. And on Saturn, they're seeing things about a few kilometers, because Saturn is, farther away, so it's more difficult to see small pieces. But definitely we are missing a lot of these. So we probably have still hundreds of objects to discover, which is a very good news for me as an orbit fitter. That is a job security. So I am not complaining for more moons.
Well, those big old gas giants, obviously they've got diverse ecosystems, they've got moons, they've got rings. But if you go a little further out, we've got our ice giants out there. Now, you brought up the poetic name. I am partial to Uranus's moons, which are named after the works of William Shakespeare and William Pope. Alexander Pope, not William Pope, William Shakespeare, Alexander Pope. The inner moons that are close to this planet, do they have the similar outline? Are there outer satellites in some strange orbits?
Well, yes and no. So you have the same kind of general outline. You have the inner moons, the regular moons, and you have the outer moons, but both Uranus and Neptune are weird, they're peculiar little systems, or big systems. So let's start with Uranus on the next slide, please. And we'll be moving from outside inwards. So you're seeing the realm of the outer satellites. We know only 9 of them at the moment. Margaret is the only prograde one. These are orbiting at huge distances from the planet. We're coming in. These are 5 regular satellites of Uranus. But then the story really gets interesting as when we start talking about these inner moons. There are 13 of them. They're small, but extremely densely packed orbits. So imagine having 13 moons that would fit within 1/4 of the Earth-Moon distance. And these moons are kind of, they're small, but they still have mass, and they kind of keep bumping at each other. And to make things worse, they are in a, some of them have integer relationship between their orbital periods. And these states are called resonances. And so what that, for example, there are 2 moons. There is Cressida and Bianca. They're in a 16 to 15 orbit-orbit resonance. What this means is that the inner moon, Cressida, goes around 16 times. The outer one, Bianca, goes around 15 times, and they catch up. And because, this happens periodically and regularly, so sooner or later their orbits start changing enough that they start colliding. These moons start colliding. And when dynamicists run studies, and I told you they like to run these long studies for millions of years, they see that this system is kind of recyclable. It goes through periods of, the moons colliding. You have a temporary system of rings, and then they all coalesce again into moons. So we don't know how many times, Uranus went to this having system of rings, having system of moons, and back and forth. And even today, you have a very faint ring between the moons called Portia and Rosalind. So interesting kind of phoenix-like system that keeps, going through these cycles.
Well, let's keep working our way out there. Let's get to Neptune. Voyager 2 flew past in 1989. I gotta love this image of Neptune's giant moon Triton. So if we bring up number 10, yeah, there it is. You can see evidence of nitrogen ice volcanoes on its surface. So how unique is Triton, and are there other notable moons in the Neptune system?
Well, Triton, as I said, it's really neat. I mean, it's huge. This is 2,700 kilometers in diameter. So, and given how massive it is and everything, this looks like a regular moon of Neptune, kind of that formed with the planet itself. But then you look at its orbit, I always go back to the orbit, and it tells us a very different story. So let's take a look at the orbit of Triton on the next slide. And so, yeah, this is what you see. So you see these little moons in yellow. Those are your well-behaved inner moons. Everybody's in circles and, lined up with the planet equator. And then you have Triton. And Triton is obviously aligned. And not only aligned, it's going the other way. So the leading theory is that Triton is actually a captured object. It's a captured Kuiper Belt object, something similar to Pluto. And this capture happened early in the solar system history, and as a result, it completely destroyed the original population of the moons of Neptune. And let's take a look at the close-up on the next slide of the inner moons of Neptune. So next slide, please. Yes, so these are not original moons of Neptune. These are, again, Neptune probably ended up, the original population probably collided between themselves. Neptune had a system of rings. And then this is what happened afterwards. They coalesced from these rings into, again, clumps that we call moons. There are 7 of them, again, very tightly packed system. The entire system would fit within 1/3 of the distance from Earth to our moon. They orbit really fast, like Proteus, the outermost moon. It takes it a little bit more than 1 Earth day to orbit the planet. But weird little system. But even bigger puzzle, I'm going to show you on the next slide. And let's see, next slide. Yes, this is a moon called Nereid. And if you remember in the beginning of your talk, I was showing you my fit to orbit of Nereid. There are those residuals. And Nereid, there is theory, it has this very distant, elongated orbit. It's a prograde moon. And the theory is that it could be the last original moon of Neptune, that Neptune had before capture of Triton, and that it got scattered into this distant orbit after kind of Triton barged into the system. Nereid is fairly large. It's about 360 kilometers, and it's orbiting around the planet just under 1 Earth year, about 360 Earth days. I don't want to forget about my outer satellites, so let's go to the next slide, because that kind of, this is probably my, the favorite system of the outers. I already mentioned, so Neptune has the largest Hill sphere where it can capture its satellites. And this is what I mean large. You see the scale here? This is 1 astronomical unit, so this would be between distance from the sun to the Earth. There are only 5 of them that we know of. There are definitely more out there, but they're very hard to find because they're very faint. They're not that large, and surveys, really have to dig deep to find them. This one that you particularly see, this one called Neso. Neso takes 27 years to orbit around Neptune, and we actually have only data for like 10 years. So a lot more data to be collected here, a lot more to learn. And I'm saying this is, it's really a great story with these outer moons of Neptune.
A lot of great information tonight, and a lot more information to come down the road as you keep studying and exploring these. As we're getting closer to our audience questions, is there anything else you'd like to say about the work that you do?
Well, so far I was telling you why orbits are important in order to learn about, the science of the system, about the origin of the moons and their dynamical evolution. But, orbits are very practical things as well. They're important for the missions. Because in order to fly a mission, you need to know where your targets, your destinations are. So let's take a look at the next slide, because I want to tell you about one of my favorite missions, and that is New Horizons. That the spacecraft ended up flying through the system of Pluto, exactly through the bullseye of the system, in 2015. And the spacecraft at that time was 9.5 years on the road, so a long time, and it was moving incredibly fast. This was like, bat from hell. It was like 13.8 kilometers a second. And so you rush to get to Pluto, and then all the data are collected within like several hours. So those are your best data, the highest resolution ones. And you need to know where everybody is in order to correctly point your camera. And you also, you want to know that you're not going to collide with something as you're going through. So every mission has a similar story like that. It's incredible feat of engineering. It takes hundreds of people and many years to complete. But ultimately, they all start with the same thing. They need to know where their destinations are. And in a solar system dynamics group, we are the map makers. So we like to think that we are very important for the missions. I always like kind of to say that the starting story of every mission begins with the same sentence. So kind of something like, in the beginning, there was a map. So.
In the beginning, there was a map. I love that. Lindsay, the chats have been busy. What questions do they have about map making in these orbits out there? What's going on with our audience?
Absolutely, Marina. I have to say, I am not the only one who's been over the moon about your talk. So Shavash on LinkedIn asked, is there a probability of Earth catching a natural satellite, and perhaps would it orbit in an irregular manner?
Oh, yes, we have mini-moons. So Earth has mini-moons, and just recently one such object was captured. So Earth knows to capture these tiny little asteroids. The last one, and I don't remember exactly, it was very recent. It was 2020 something. But these moons spend about several months to a year orbiting in a very, very regular orbits, and then they take off. And they start orbiting the sun again. Those could be great targets for space missions because it's easy to get to them, and perhaps you could perhaps something like that we are going to see sometimes in the future.
Awesome, Marina. Paul on Facebook is asking, would it be reasonable to assume that some of the moons of Jupiter are a part of what used to be a ring?
Yeah, so so Jupiter has a ring. It has there is Io is spewing a whole bunch of particles, and also the inner moons that I mentioned that are orbiting closer to the planets than Io. They're also sources of a material. They're thought to be sources of material that are creating this very faint rings of Jupiter.
Great. Fidelo on YouTube asked, if you, Marina, could pick any target for a probe mission, what would it be?
Oh, so many targets. Well, Triton would be a natural choice. That is a weird moon. As I said, you kind of have a Kuiper belt object caught around Neptune. And I would also, Nereid always kind of piques my interest because it could be an original satellite of Neptune. It's perhaps a very different object. So it would be interesting to Triton. I think Triton would be something that I would like. But there are many other moons.
Thank you. Dean on Facebook would like to know, how large are the objects that you've found?
So I'm not sure objects. So I don't know. So I can tell you if he's asking about current surveys. Around Jupiter, I mentioned that the outer moons of Jupiter that are currently being found, they're about 500 meters in size, so quite small. And Saturn, outer moons of Saturn, they are slightly larger because, as I said, you can't go as deep. Saturn is further away. So surveys have been finding objects that are about a few kilometers in size, and we are estimating there should be probably hundreds of such objects.
Thank you. Zapfan on YouTube asks, are any captured interstellar objects among these retrograde moons?
Oh, that's a good one. So I am not. I think there could be some studies out there that are wondering about that question. I think that I think there was a moon of Jupiter that they were maybe speculating, but I'm not going to guess because, as I said, it's in the literature. People are very interested. So far we had 2 interstellar objects visiting our solar system. They come in. They move at such incredible speed and they come in and out so fast. It would be really not easy to capture such thing, even in heliocentric orbit, let alone it would have to be perfect storm that a planet ends up catching it. But I think it's. I'm going to check out after this talk. Basically, if there are some papers out there, I think that somebody was already looking into that. But on top of my head, I can't. I don't know.
Thanks, Marina. And Jimmy on Facebook asks, is there a minimum size requirement to be considered a moon?
Is there a minimum size? Well, I think that as long as you're a small object orbiting a larger object, you're considered a moon. I can tell you that I work on asteroids, and we have some very tiny binary near-Earth asteroids. So I think that the smallest moon that we observed with radar is only maybe 10-20 meters. So it can be really tiny. So you have presumably near-Earth asteroids. They come in all sizes. And the smallest binary, yeah, perhaps the primary is maybe a few tens of meters, and then you have a satellite is maybe 10 meters. So it's just a kind of it's very loose definition.
Jonathan on LinkedIn asks, what kind of mapping software do you use?
Yeah, this is custom in-house software that we built. So this is kind of JPL software that's been developed for many decades and tested on many moons and many missions.
All right, Lindsay, I think we've got time for one last question. Oh, yeah, one last question.
Okay.
Sounds good. Thank you, Brian. And Cliff on Facebook asks, does our moon have any mini moons?
Oh, does our moon have any mini moons? So not that I know of. That's a good one because it's kind of one of these kind of neat question. Can a moon have a moon? And dynamically it can. The answer is yes. But it is probably not long-lived because kind of everybody's tugging on it. You have a planet that's tugging on it, and so it's dynamically it's possible, but not for a very long time. Good one.
Well,
good one.
That was a great one to end on. I'm happy we got to so many questions tonight. That was wonderful. But that is all the time that we have for tonight. Go ahead and join us next month for our special Earth Day talk. I'd like to thank our speaker, Dr. Marina Brozovic, for taking the time to share her expertise with us this evening. It was wonderful talk and such great animations. I just loved all of it. Thank you to Lindsay and everyone behind the scenes who make these talks possible. And finally, a big thank you to all of you who join us each and every month. Stay safe, stay kind, stay curious, and we'll see you in April.